Hey everyone, welcome to Computer Vision. We're going to be hopping into a deep learning lecture here shortly. I think it's lecture 21. I think it's lecture number 21, I believe. My video is off. We're having some connection issues today, so probably just audio and screen share. So I'll do a screen share in 1 second, but Arvind and Rohan, any announcements or anything from you guys?
No, Professor.
Okay, all right. Well, I hope everyone, go ahead.
Yeah, one announcement actually. So Rohan might not be available on Friday, that's what he said. So I request the groups which have meetings with Rohan, please book your slots if it's possible on Tuesdays and Thursdays.
Okay, great. And is that just for this week or is that going forward?
Just for this week, Professor.
Okay, great. Yeah, so
Only for this week.
okay, great. Okay, great. So yeah, if you have a meeting with Rohan this week, please book
And
Tuesday.
next week we don't have any meetings because of the Thanksgiving break.
Of course, of course. Perfect. All right. Anything else, Arvind or Rohan?
No, Professor.
Okay.
No, nothing. That's it, Professor.
Okay, easy. All right, great. Okay, so let me go ahead and share my screen here. Welcome everyone. Hope you're having a good week. It's Tuesday again already. All right, cool. All right, so we've made it all the way here to more in-depth neural networks. So you had your project stage 3 due last night. Hopefully that went well. Hopefully your FastAI was friendly to you, or whatever you were using was worked reasonably well. I'm sure you might have run into some issues, but that's generally how deep learning goes. There's some battles to fight along the way. So the next due date will be the end of this module. You'll have a programming challenge and a quiz due on the 30th. So that is, I guess, in just a couple weeks. And that will be, let's see, this is after Thanksgiving. Yep, right, cool. So you're welcome to do it before if you'd like to, but this will be the day after Thanksgiving or the Monday after Thanksgiving for that quiz and the programming challenge for deep learning. Great, and then you have just 2 more lectures with me in this module in deep learning. And then we have a guest lecture with Andrew Edelman, and he is very experienced at deploying deep learning applications. That'll be really interesting. And then we just have 1 more module after this. So we are really getting close to the end here already. And yeah, today is kind of as deep as we'll go into deep learning, and then we have a lecture on GAN, so that's always a fun lecture. So GAN stands for a Generative Adversarial Network, and that is the technology behind deepfakes and other kinds of fake images like that. So those are our last 2 lectures. I hope you've enjoyed deep learning so far. It really is a pretty powerful and interesting technology. And today we're going to get even deeper into how to make deep learning really work. So let's hop into that here. And I am in the 5th notebook number 5 here, Deep Learning in Depth, part 1, and we went through this last time, and I'll kind of pick up where we left off here. So last time we really left off, we did a bunch of stuff. We covered one-hot encoding. We talked about cost functions. We left off with this question. We talked about cross entropy loss, and then we left off with this question. Let me pick it back up here. I think this will be a good spot to pick back up. So, and I'll zoom in just a little bit. All right, maybe a little bit more. Cool. Okay, so this was one of the last things we covered on Thursday, and we talked about loss functions. And up until this point in this course, we've been using a lot of this cross entropy loss function. And I'm sorry, excuse me, we've been using much of this MSE loss function. Sorry, we've been using the mean square error or the squared error loss function. And we realize that it has some problems, right? It's not perfect. And one of the problems is that it creates these flat regions that are hard to go downhill on, right? It's hard to find the gradient and find the minimum. We walked through a bunch of math, not in a lot of detail, but just enough to hopefully give you a flavor for it. And we found what's called the maximum likelihood estimator, the MLE, for our softmax distribution, and that turned out to be this cross entropy loss function, which might look a little bit confusing. But we did this plot to hopefully clarify it and show you that this is a reasonable loss function, this cross entropy function. And we made this plot, and then I wanted you to think for a little bit. I asked you to say, okay, we've switched our loss function, right? What will happen now? So we go and train our neural network, and we have this new cross entropy loss function. And my question to the class was, when we switch out the loss function, will we achieve a higher accuracy than with the mean square error? Will we actually get a better solution? Will we achieve a similar accuracy, but we'll actually converge more quickly, right? So will the performance be similar, but we'll get to the answer faster? Or will it be basically the same? Does it not really matter what our loss function is? And I think the most popular answer was B. So you guys said, hey, it's going to achieve a similar performance, but it's going to get there faster. And this plot kind of tempts you to pick that answer. But remember, this is just a projection. It's just a shadow of the overall loss function. It doesn't show the full loss function with respect to the weights. And that's too high dimensional of a function for us to visualize. This visual is really just to get you thinking a little bit. And it turns out, very interestingly, I think, that when you change the loss function, you actually end up getting better performance. So our neural network arrives at a better solution. So this is as we train through our various epochs, our accuracy increases. And if we're using the mean square error loss function, our accuracy goes up like this and kind of levels off around 90%. And if we're using cross entropy, though, our error or our accuracy jumps up much, much more quickly. After one epoch, we're already, I think the 0 is actually the first epoch, we're already at 87% accuracy. And we end up around 95, 96% accurate just by changing the loss function. So your loss function can actually impact your performance, which is interesting, right? So it really matters how you measure your performance, because that's the function that we compute the gradient relative to. And that gradient drives optimization, right? So it really does matter. Okay, so I hope that all makes sense. We covered that last time. And now, finally, we at this point, we have seen deep neural networks, but only through the lens of FastAI, right? Only with FastAI. And FastAI is a high-level library, so it's not, if you're just using it the way that we did, it's not really clear what's going on under the hood. FastAI is great because you can quickly introspect and get inside of those models and see, but we haven't done that yet in this class, right? So we haven't really built a deep neural network from scratch, right? We haven't done that yet. And by the end of today's lecture, we're going to have mostly done that, I would say. So let's kind of get into it. And as you may know, let me actually ask the class, so maybe our first question of the day. Why is it called deep learning? Why is it not just machine learning? What is the difference between deep learning and machine learning? What would you say to someone that asked you that? Okay, so Sai says the use of neural networks, right? So that's part of the answer for sure. Hernan says more layers. Abhijit says number of hidden layers. And then, right, and this is Akansha. You're gonna have to tell me how to pronounce your name. One of these. Well, next group meeting we're in, you have to guide me through pronouncing your name. I'm looking forward to it. I apologize. But you've said that it learns from previous networks. Sure, yeah, transfer learning. Yep. So all of these answers have validity to them for sure. What I would say really is that machine learning is just the idea of learning from data, right? And within machine learning, one way to do that is with a neural network. And a neural network can have one or more layers. And when we have many layers, or let's say more than 2, for example, we would call that a deep neural network, right? So really, it mostly just means more layers, right? That's the big difference, just more layers. That's really the only big differentiating factor, in my definition at least. And I think most practitioners would agree. Okay, so if that's the only difference, right? And notice we've been training neural networks, right? Like we just trained one. Where is our architecture? Here it is. So how many layers does this neural network have that we trained? Let me zoom in a little bit more. How many layers does this neural network have? So I see a 1 and an 800. Good guesses, but the answer is 2. So each of these linear. So it has 800 hidden units, which maybe is what you're thinking of. But yeah, it has 2 layers. Each of these layers represents, each of these linear functions represents one, and I guess I do say it actually, don't I? I kind of gave the answer away. That's a good call, Sai, right? I should get rid of this for next time. So it only has 2 layers, right? Cool. So if I want to make a deep neural network, can't I just do something like this, right? So can't I just say, okay, here's a new model. Remember the input is 784. Why is the input 784 again? Why is that the dimension of our input? Thank you, Monica. Yeah, so this is images. What is the name of the data set we're using again? What data set are we playing with right now? MNIST, thank you. Yep, perfect. So our input has to be 784. And notice that our output is 10. Why is our output 10? Why is the dimension of our output 10? 10 classes, yep, because there's 10 numbers, right? The numbers 0 through 9. Perfect, good. So what have I done here, guys? All I've done is I've just made a bunch of hidden units or hidden layers, right? I have 5 layers total now, right? And these numbers, right? What does this 1024 represent? What does that mean? What am I controlling with that number? Yeah, it's the number of neurons in that hidden layer, right? So I could have chosen 512 or something, right? I could do something else, easy. I've just made the design decision to go 1024 and then 128 and 64 and 32. And we'll talk about those decisions more later as we have time. But at this point, you know, it's just an educated guess at what might work well. And we have our sigmoid activation function at the end. Yeah, so Monica says, why always even numbers, right? And these actually aren't even just even numbers. These are even more special than that. What's more special about these than being just even? Yeah, they're powers of 2. Yeah, these are powers of 2, yep. So it goes back to, part of it's just a personal preference. You can certainly use odd numbers, you know, no one's gonna get mad at you. But there is, on GPUs, there's a quote earlier from Ian Goodfellow's book that we talked about way at the beginning of this lecture last time. We said that for GPUs, it is common to use powers of 2. That's more for batch sizes, but I tend to use it everywhere. So powers of 2 can be more efficient on GPUs. It's not always the case, but it's just a pattern that you'll see a lot, and it's certainly a pattern that I use, but they could be odd numbers, it could be not powers of 2. It's just a design decision, and in some cases it will be more efficient to use powers of 2 for things like this, but not always. So yeah, good question. The new Mac has a 7-core GPU. I didn't know that. Wonder why they chose 7. That sounds terrible. Why would they choose 7? That's interesting. Okay, so let's train this thing. And I think manufacturing defect. Yeah, every new Mac has the same defect. Can you imagine? Oh my gosh, it was supposed to have 8, but it has 7. So I'm going to go ahead and start training this now in my little MacBook, and we'll see how we do. And we're going to train this network with 5 layers, and really we're just trying to do deep learning, right? We're saying, okay, deep learning is just a network with multiple layers, so let's see what happens. So I'm optimizing here. I'm using the cross entropy loss. I've added a little visualizer. That's what all this code here is, so we can visualize performance as we go. So we've already started to train here. And as my plot is updating as I'm training, I'm using this display library in Jupyter Notebook to be able to update my plots as I go. So this is our loss as we train. And actually, before I get into this into too much detail, remember that our last network that we trained, it was only 2 layers deep, right? It was 2 layers deep, and it achieved an accuracy of 96%. So by going to 5 layers, right, I would hope that our performance increases, right? You know, maybe it's 97, maybe it's 98, maybe it's 99, right? So go ahead in your head. I should have made this a poll question. That'd be kind of fun. We'll do a poll in the next section though. But like, how well do you think we'll do by going to 5 layers, right? We're at 2 layers now. We're gonna go to 5. What is your prediction, right? What do you think? And actually, just for fun, throw it in the chat window. Any predictions? What will our new accuracy be? So we're going from 2 layers to 5 layers. The baseline is 96%. Any predictions? What will our new accuracy be? So Hernan is predicting an exact increase of 2.67%. I love the precision. Any other predictions? Any skeptics out there? So Sean says decrease. That's fun. Okay, if we did decrease, Sean, why do you think we would decrease? What could cause our performance to get worse? Yeah, Monica said it, right? Overfitting. We could overfit, right? Why would this network be more likely to overfit than the last one? What would make it more likely? Not enough data, but what has changed though, right? It's changed. We have more parameters, right? So we have a more complicated model. The more complicated your model, the more parameters, the more likely you are to overfit. So we should keep that in mind. So Sai says convergence might be slow, more computation might decrease for the same number of iterations. Totally, yeah, okay. So we have some skepticism, right? So let's get into it. Let's go see how we're doing. So here's our plot. We've made it through 9 epochs. And what is an epoch again? So Pooja says pass. True, pass through what? Pass through all of our data. Yep, perfect. So it's a scan through our whole data set. Great. So we've been through our whole data set 10 times now, it looks like. Okay. And notice that I'm plotting our accuracy on our training set and on our testing set. And oh, look at that, right? We just achieved 100% on that epoch accuracy on our training set. What's the problem though? What do you see? So our training accuracy for that epoch is 100%, right? But what is our test accuracy? Yeah, it's overfitting, right? Yep, totally. So loss is coming down. We're doing okay, but we're actually doing worse, right? So our baseline was 96%, and like right now we're at like 95.7. So we're actually not doing any better, which is kind of depressing, right? So if you were skeptical, that was for a good reason. We haven't quite done all the things we need to make deep learning really work. We're getting there, we're getting close, but we haven't done all the little things we need. We've got a good loss function, we're making progress, but there's still a little bit of work to be done. And this reminds me of a really fun comic that I like a lot. You might think it's funny. If not, that's okay, but I think it's really funny. So in the history of neural networks used to be part of statistics, and statistics is very theoretical, and you have all these complicated ideas like the VC dimension and things like that. And when neural networks came around, kind of the impression of some deep learning work was that, hey, this is not serious science, you're just stacking more layers, right? So this is just a fun comic where the statistician is saying, gentlemen, our learner overgeneralizes because the VC dimension is all very serious, and here's your deep learning practitioner just saying stack more layers. So like all jokes, there is a little bit of truth to it. So I wanted to make sure that by the end of this class, you are not just stacking more layers just to have more layers. And I really like this plot here too, because it has layers on both axes, which I think just kind of cracks me up. Okay, cool. So what do we do then if we're not just going to stack more layers? And the clown drawing is funny. I think it's very good. Yeah, I don't know who made this comic, but I really like it. Yeah, definitely. Okay. So let's see here. Right, here's the other thing I want to emphasize. So we just achieved an accuracy of like 96%, maybe 97. Maybe I think it's going to keep training. Maybe it gets a little better, But this would be impressive. However, way back in 1998, which I was 11 years old. I don't know how some of you guys might not have been born yet, but a long time ago, right? This researcher named Jan LeCun, he is the one who kind of made this data set. He achieved an accuracy of 99.05%, and this is in 1998. So he didn't have a GPU, right? He achieved a way better accuracy 22 years ago, right? So what I want to get into is how did he do this, and what are the lessons from that? So that's how we'll start the next lecture. How did Jan LeCun, this researcher, how did he obtain an accuracy of 99.05% on the same data set back in 1998? So that's what we'll get into now. Okay, so we'll hop to our next lecture here. And hopefully you've had a chance to look at some of the reading from Ian Goodfellow's book and the AlexNet paper. And yeah, let's do a little story. So yeah, this story is about Jan LeCun. So Jan LeCun, let me show this fun video. So here's a video of Jan LeCun back in the, I think this is 1993. Yeah, so in 98, he really achieved that top level accuracy. But before that, he was building these systems that do image or digit recognition. So there's the demo, pretty cool, right? By 1993 standards, this was pretty fancy technology. So here he is demonstrating his digit recognition system. And I just love old videos like this. I think it's pretty cool. One day people will laugh at old videos of us, right? But here's Jan LeCun back in the 90s. Now, I'd like to just ask the class real quick. Well, let me just give you a little bit of background. So this was at Bell Labs and in the 80s and 90s where Jan LeCun was working. Before Jan LeCun joined Bell Labs, he worked in Geoff Hinton's lab at the University of Toronto. Remember, Geoff Hinton is a character we've heard of before, and we'll hear about him again. And I think the last thing I'd like to say, yeah, does anyone know what Jan LeCun's job is now? Does anyone know what he does now? So Jan LeCun is Facebook. Yep, that's right. He is director of AI research at Facebook. So he, both Geoff Hinton and Jan LeCun, he's not the YOLO guy. The YOLO guy is, what's that guy's name? It'll come to me in a second. But yeah, Jan LeCun is, there's really three folks, Yoshua Bengio, Jan LeCun, and Geoff Hinton. They won the Turing Award for their work in deep learning, I think last year. their work has really come full circle, and now they kind of have their pick of jobs. So neural networks are very relevant in all kinds of work now, including at Facebook, where Jan LeCun works now. So all of these early researchers have, their investments and time spent researching have really paid off. So yeah, Jan LeCun is the director of FAIR now, the Facebook AI Research Laboratory. Okay, so what I really want to get at though is this. So that's Jan LeCun. I definitely recommend looking at his work. He has a really good podcast. He was interviewed on Lex Fridman's podcast last year or earlier this year. It's a really interesting one. So interesting guy to listen to. But let me get into his idea, right? So what idea did Jan LeCun have back in the 90s to do such a better job than us? So he actually wrote about this idea, I think actually back in the 80s. I think this paper I'm showing you, it's from 89. So I was 2 years old when this came out. So he wrote this paper about ways to improve neural networks, especially for image recognition, for image tasks. So what he talks about in this paper is a special thing he calls a weight sharing technique. And I'd like to emphasize a point he makes. So he says weight sharing not only greatly reduces the number of free parameters in the network, but it also can express information about the geometry and topology of the task. So this might sound kind of fancy, but it's really a simple idea. What Jan LeCun did is he did something smarter than just using linear, fully connected layers. That's what he really did. And we'll get into how it works. But what he's trying to do is take advantage of kind of how images work to make a more efficient and smarter neural network. So let's get into it here. So this is the big idea here is a convolutional neural network. And Jan LeCun didn't call it a convolutional neural network. We only called it that name later. He called it this weight sharing technique. But CNNs are really the core of most modern deep learning for image analysis. And a CNN is a little bit different than what we've been doing thus far. And I'll get into exactly why in a second. So I guess I'll get into exactly why now. Yeah, let me get into exactly why. So let me hop back to here, right? So with our neural networks so far, right? Here's one of our neural networks, right? So I keep asking you about this 784 because I want to remind you that the reason we have 784 input neurons, basically, or inputs, is because we take our full image, it's 28 by 28, and we unravel it into a vector, right? So every single pixel in the image gets passed into the first layer, right? Now, being in this class for a few months, I hope you have some better understanding of how images work and how kind of image processing works. And it turns out that when you're analyzing an image, there's some disadvantages to trying to look at the whole thing at once. And by doing this, we're really looking at the whole image at once. I hope that makes sense. So every single pixel in the input in the image is being multiplied by a weight in this linear layer, all pixels at once, right? And it turns out that what you can do that's a bit smarter is instead of looking at all the pixels in your image at once, you can break apart your image into these little grids, and you can take a kernel and you can move it over your image, and you can just process little neighborhoods at once. So that's really the idea of a convolutional neural network. And I'll get into this cross-correlation thing in a second, but this is really the idea, and we'll get into it into more detail. But the idea is that instead of processing the whole thing at once, I'm going to process it in chunks, and I'm just going to start by looking at little neighborhoods. That's the idea of a convolutional neural network as opposed to just a regular, fully connected neural network. And convolutional neural networks are not called fully connected because what really happens is you don't look at all the inputs at once. So you don't have a full connection from one layer to the next. That's the idea. We'll get into that in a little bit more detail. So taking advantage of topology, right? You're using the local, right? You're just looking at neighborhoods. That's what the topology thing means in this context. So good point, Sai. I'll just say briefly that way back in Module 1, we talked about this idea of cross-correlation. So cross-correlation, we called it filtering as well, is when you take a kernel like this, you slide it over an image like this, and for every location, you take a dot product, right? So you take all these values, multiply them by the corresponding values, add them all together, get a result, put it here. That's called cross-correlation. Convolution is actually very similar to cross-correlation. So this is the cross-correlation formula. This is the convolution formula. So just take 1 second with me. Look at these two formulas. I know I'm throwing a little bit of math at you, but hang in there. Here I'm sampling the image basically. Here I'm sampling the kernel, and I'm taking, this really represents the dot product of what I'm doing here. So just looking at these equations, can anyone tell me what is the difference between cross-correlation and convolution? What do you see different between these formulas? And what does that actually mean about how we're processing the image? Yeah, first of all, what do you guys see what's different between this equation and this equation? Yeah, so going reverse, totally. So you see these minus signs, right? You see these minus signs. And the m and n, that's just iterating over our rows and columns, basically. What this effectively does is when you do convolution, you can think about it like flipping the kernel. So I know that I have the minus signs here inside of the image bracket. That's for a reason. But really, the way I like to think about it is that you're doing the same exact thing as here, but whatever the kernel is defined as, you're just flipping it. So you're flipping it vertically and horizontally in convolution. Now you might be thinking to yourself, Stephen, why the hell would you do that? Who cares, right? So it turns out mathematically, if you do convolution instead of cross-correlation, it makes the operation commutative, which means you can change the order and have the same result. So if I convolve A with B, it's the same as convolving B with A. So mathematically, convolution is nicer. But in practice, most modern deep learning neural networks implement cross-correlation. It actually doesn't really matter because you're going to learn the weights anyway, so it doesn't really matter if you flip. So really, they shouldn't be called convolutional neural networks. They should be called cross-correlation neural networks. But we're going to call them CNNs, and we're going to say convolutional neural network. But just to be technically accurate, and so you know what you're talking about, really modern CNNs implement cross-correlation, which is where you just take a kernel, slide it over an image, take all the dot products, compute the result. That's what these networks do. So let's get into that into more detail, because I don't think I've explained it in enough detail for you to feel like you can implement it yet, I'm guessing. So let's get into it. These are some notes from Stanford's lecture on convolutional neural networks. So this is a great lecture I'd recommend watching if you want to dig deeper. This lecture is from Andrej Karpathy at Stanford. Does anyone know what Andrej Karpathy's job is now, or Andrej Karpathy? Anyone know what he's up to now? Uber, good guess. Did he move to Uber? Last time I checked, he was like director of AI at Tesla. But he used to be I'm not sure if he was a TA or a professor when he gave this, but this is a great lecture by him on kind of the nitty-gritty details of convolution. And I've stolen a few slides from him. Tesla, okay, yeah, cool. So he's at Tesla, great. Here we go. So let's talk through how this convolution thing works in a little bit more detail, and I'm borrowing these slides from Andrej Karpathy. Okay, so we have an input image. Here it is. Why is the depth of this image 3? Why would the depth of our image be 3? Yeah, it's color. Great. It's a color image. We'll assume it's color. Great. It could also be black and white. You'd have 1 in that case. And here's our filter. This is like the thing we're gonna learn the weights inside of our filter, basically. This is like our layer. And when we do convolution, we basically take this little filter, and it always has the same depth as our input, and we take it and we slide it across all the locations. For each of those locations, we compute a dot product, right? And Andrej Karpathy points out here that, hey, this is a 5 by 5 by 3 filter, so it has 75 weights plus 1 bias term, so 76 total parameters. We compute one number for each of those operations. We slide it across our whole image. The output here ends up being 28 by 28. I hope it makes sense why it gets smaller, and it doesn't have to get smaller, but in this case, because we aren't padding, we kind of bump into the edges of the image, so the result gets a little bit smaller. And we call this an activation map. So we do this operation, we get this activation map thing. In case you remember, this is the same exact math as what we did back in the first module. This is exactly like filtering, same thing. Now what's a little bit different here is that we are going to have multiple filters, right? You're going to have multiple filters. So we did this first one, right? We're going to have a second one. And that's going to learn another, we call it an activation map here. And in many cases, you'll have many, right? But here we'll just use 6 as the example. In some cases, we'll have many more. But what we do is we have 6 different filters in this case. They each process the image to create an activation map. And we end up with 6 of those because we have 6 filters. And this kind of creates, we could think of it as like a new image, right? But now it has like 6 color channels, and they aren't exactly color channels, right? They don't really mean color in the way that we think of color, but it's not a bad way to think about it, right? So when we do convolution, we're taking this little kernel, we slide it over our image, and we do that for as many kernels as we have. And in practice, you'll see sometimes we're going to have hundreds of kernels, and we get this new volume of data that we're going to continue to process in following layers of the network. So that's the idea of a convolution. So when someone says convolutional neural networks, they mean that instead of the layers being fully connected, where you have like the whole image being processed, you're processing the image instead in these local neighborhoods to make these activation maps. That's what someone means when they say a convolutional neural network. Now we'll get into this into even more detail as we explore Yann LeCun's solution from the 1990s. But first, I just want to let you know that there's a bunch of different ways you can actually do the convolution. So what we just kind of saw was just like one step. You can also do a bunch of other stuff. So these are some nice animations. There's a really great paper. I forgot who the author is. Who's the author of this paper? Dumoulin and Visson. Okay, yeah, so this is a really great paper. It walks through the math of convolution. This is out of the scope. I'm not going to quiz you on this kind of thing, but if you're curious or you need it for your project, this paper really does a really nice job of describing all the different ways you can do convolution. In practice, in your project, if you're just training models, you don't have to worry about this too much. FastAI will usually make a pretty good choice for you, but it might matter if you're doing a custom network, for example. So I want to make sure you're at least aware of it. So like I said, there's a bunch of ways to do this. You can add padding to your input image. So here the blue is the input, the green is the output. So you can add padding to your image if you want the image size to stay the same. You can do what's called half padding. You can do striding. When you do striding, you take steps that are bigger than 1. So there's a bunch of things you can do, different ways to do our convolutional step. And we'll come back to this if we need it, but I just want to make you aware of that and give you a resource in case you need to learn a little bit more about that as part of your project or as part of your research. Okay, so I promised that I would explain how Yann LeCun's network from the 1990s, I said I would explain how is it so good, right? How is it done so well? So I'd like to show you in more detail how it works, and I think that will help us understand how it did so well. So we've explained that convolutions take advantage of the topology of images, which I hope that makes sense. And now let's get into more detail here. So here's a question for you, first poll of the day. So this is a figure from Yann LeCun's paper where he explains it's called the LayNet5 network that he developed to classify images in the IMNIS dataset. And I just want us to think about the first layer for a second. So notice that he's starting with 32 by 32 images. He's taking a convolution of that image with a kernel. His kernel is 5 by 5. This kernel is 5. I think all the kernels are maybe that one is 3 by 3. I'm not. We'll get into it in a minute. But this first kernel is 5 by 5. Our input is grayscale, and we're going to produce 6 different feature maps from these convolutions. So we have 6 filters. That's going to be our first layer, right? And I want you to take a minute, please, and think about how many parameters, right? How many trainable parameters are in just this first layer? So the first layer, that just represents the step from here to here, right? That's just our first layer. And I want you to think for a minute, right? How many trainable parameters do you believe are in that first layer? So let's open up a poll when you guys are ready, please. And yeah, give us your best answer. What do you think? And I think we're including bias, I believe. Yeah, I think this does include bias. So yeah, how many trainable parameters are there in that first layer? All right, thanks guys. Okay, so the most popular answer is C. The second most popular is B, and then finally we have D. Okay, let's get into it. So I have an explanation down here, I'm sure. And actually, do I want to? Yeah, let's go ahead and talk through it now. So let me actually go back to this for a second, right? Because it's actually very, very similar to this example. So the only difference here is that instead of a 3-dimensional filter, we have just 1 dimension because our input is grayscale. So here's our network again. So each of these kernels is 5 by 5, right? So in a 5 by 5 kernel, basically that consists of a set of 25 weights because it's 5 by 5. Those 25 weights are multiplied, and we take a dot product with the pixels, right? So you have 25 weights for each kernel, plus you have 1 bias term. So you have 1 bias term, so 26 weights for each kernel. And then you have 6 kernels because you have 6 feature maps. So the answer ends up being 26 times 6, which is 156. So the answer to this is D. If you didn't get it right, hang in there. I'm going a little bit fast here. I would review this lecture a little bit more. This is definitely the kind of question I would ask you on a quiz to kind of tell me how many parameters would be in a layer like this. So do come back and review this. Ask the TAs or ask on Piazza if it's confusing. But that's the idea, right? So we have 6 of these kernels because we have 6 feature maps. And each of those kernels, because it's a 5 by 5, is going to have 25 parameters plus 1 bias term, so 26 parameters. And it's just 5 by 5, not 5 by 5 by 3, because our inputs are grayscale. Okay, hopefully that makes sense. Now, what I want to get at, and I'm trying to give you some reasoning, a way to think about why LayNet is doing better than our fully connected network. So here's the network we trained in our last lecture. And let me just ask you this, right? So how many parameters approximately do we have in our first layer, right? So LayNet 5, the network we were just talking about from Jan LeCun, it had 156 trainable parameters in its first layer. What about this fully connected network, right, that we trained last time? So let's throw up another poll, please, guys. So take 30 seconds or so. Approximately how many weights are in this first fully connected layer? Okay, thanks, guys. So the most popular answer is B. I got some C's and we have some D's. Okay, cool. So what I'd like to show you actually, let's go back just for a second. So I'm going to go to GitHub/UNCCV / oops, there we go. Let's go back to the Neural Networks Demystified series real quick. Because I want to help. So some of you guys got it right. Great job. Some folks miss it. I want to make sure I explain clearly what the answer is. So this is a fully connected layer. And let me go to, I think I want to go here. So hopefully this will load in GitHub okay. If not, I'll run the notebook or something. But I just want to show you one figure really quick, because what we have here is a linear layer. This is a fully connected layer, and it has 784 input units, and it has 1,024 neurons, hidden neurons in that layer. Oops. All right, we'll see if this does any better. Yep, perfect. So all I want to show you is this. Here we are. Cool. So this is a neural network, right? This is a fully connected layer from here to here, and there are 2 input units, right? 2 input units, and there are 3 hidden units, right? And how many parameters are there in the first layer of this neural network? 6, right? There's 6 connections, right? And you could arrive at 6 by counting the lines, or you could do 2 times 3, right? So 2 times 3, because everything's connected, it's fully connected. 2 inputs, 3 outputs, so 2 times 3. Okay, so back here, right, how many inputs are there in this linear layer? There's 784, right? and how many outputs are there? There's 1,024. This is kind of close to 1,000 times 1,000, not exactly, but roughly. And what is 1,000 times 1,000? I should offer a prize on this. Yeah, it's 1,000,000. Yep, thank you, Ravina. Great. So yeah, it's 1,000,000. So the answer is 1,000,000. So the first layer of this neural network looks kind of innocent, but it has 1,000,000 parameters, right? That's pretty crazy. Actually, plus bias, there's some more, right? But I guess 1,000,000 is rounding anyway, but roughly 1,000,000, right? It's got a lot. So the answer is D to that question. And let me ask you this then. So we've seen LANET 5, right? This only has 156 trainable parameters in the first layer. And we've compared it to our own kind of simple deep learning network we made, and it has 1,000,000 parameters in the first layer, right? Why would less be better, right? Why might less parameters be better? Why do you think? So LANET 5 is going to perform better than our neural network. Why are less parameters better sometimes? Yeah, so a simpler model. So the time is important for sure, but Ravina says overfitting. Yeah, absolutely. Yeah. So the more complex our model is, the more likely it will be to overfit. And having 1,000,000 parameters makes it a very complex model, right? So the less parameters we can get away with, the better we will do. You still need as many parameters as the complexity of the problem requires, so that can take some tuning. But in general, 1,000,000 is a lot, especially for this problem. Okay. So that's idea one. So this idea of convolution, that's probably the most powerful idea in LANET 5. And we're going to implement LANET 5 pretty soon. Yep, right down here. But there's one more idea I wanted to share with you first. And this is so convolution is a very critical idea in modern deep learning models. But there's another idea called pooling that I want to discuss with you, because this is also very common and it's an important tool in modern deep learning networks or deep neural networks. So in Jan LeCun's paper, he includes what's called a subsampling layer. And a subsampling layer, today we'd call it a pooling layer. And he has it right here in his picture. And notice that our 28 by 28 feature maps, after subsampling, become 14 by 14, right? So they become half the size. So what's happening? How does this work? So what's really happening is this idea of pooling. And there's different ways to do pooling. And the two that we'll talk about in this class are max pooling and average pooling. So in max pooling, you take little neighborhoods of pixels and you take the maximum value, right? So 5 is the biggest in this neighborhood, 6 is the biggest here, 7 is the biggest here. And in average pooling, another way of pooling, you just take the average value, right? So Jan LeCun, I believe, uses max pooling, I believe. And this is a very common idea in deep neural networks. And it does a couple things. So one thing I want to point out, there's something I want to point out about the sensitivity of these networks. So this network, you might have noticed this when you were doing the autonomous driving challenge. This network is going to be very sensitive to the location of pixels. Because if a pixel is in like the first row, 10th column, right, it's always going to be multiplied by the corresponding weight that's in the first row, 10th column, right? It's very sensitive to translation. If an image moves a little bit, you may get a very different result. When you do pooling, you take that away. What you're doing is, because you're kind of collapsing the image down, right? It makes it what's called more translationally invariant. And what that means is that if the input moves, the output stays the same, right? If you do max pooling, right? If this 5 had been over here, right? If the whole image was shifted 1 pixel to the left, this pool, you'd end up with the same result, right? Because it'd still be the biggest number in the neighborhood. Let me ask the class this real quick. When is pooling a good idea and when is pooling a bad idea? So when do you want translation invariance? For what kinds of problems do you want to get the same answer when the input shifts? What do you guys think? When is translation invariance helpful? So object detection, yeah, I agree, absolutely. Let's think a little, totally, yeah, I agree. Object tracking, sure. And actually, there might be a little more detail we could add there. Feature extraction, sure. Let me ask you this, let me back up a little bit. What about, so the task we're discussing today is a handwritten digit recognition, right? So recognizing that a 3 is a 3 in an image, or a 3 is a 5, or recognizing digits in images. Do you want the property of translation invariance for classifying handwritten digits? Is that a good property or a bad property? It's good, right? Why is it good? Why is translation invariance good for a digit recognizer? That's right. The image can shift. So yeah, Hernan, great, perfect. The digit can be written anywhere. Yeah. So Nick, thank you. Sean, great, absolutely. Right. So, oh yeah, but Sai actually raises a very good point, right? So let's discuss here. So you want some kinds of shifts, right? So shifting left. So if I take a handwritten 3, and I move it to the left by 3 pixels, it's still a 3, right? But Sai says, okay, but what about inversion? What about flipping, right? So we do not want reflection invariance, right? But here, remember, we're just talking about pooling. We're not talking about reflecting an image. We'll talk about that later. So here, the translation invariance is good. Now, if you're training a neural network to actually, so some of you guys said object detection earlier, which I kind of disagree with actually now that I'm thinking about it, because let's say that you were training a neural network to do like a lane detector for an autonomous car, right? You're trying to have it detect the lane markers. You actually don't want translation invariance, because if a lane marker or steering angle, right? Because if a lane marker moves in your image, then you want the result to be different, right? That means something different, right? So you do not want translation invariance in general detection problems or steering angle, like Monica said, or like lane marker detection. Whenever you have to localize something, right? You do not want translation invariance. So just something to think about. If you're doing classification in general, pooling is good, and pooling is built into a lot of the networks you use in FastAI. But now hopefully you have a little bit of a sense for what pooling is. And this is another important idea that gets used in LaneNet 5. Okay, cool. All right, so finally, we've talked about it a bunch, right? Let's go train LaneNet 5. We'll make a few changes that Jan LeCun wouldn't have done, but for the most part, this is going to be very, very similar to what Jan LeCun would have done back in 1998 and maybe a little bit earlier. Okay, so this is LaneNet 5. And I really like slides like this. I like visuals like this, because this is a skill that I would like all of you to have, especially those of you who continue to work in computer vision. I would love for you to be able to look at an image from a paper like this and translate it into like PyTorch code, right? This is a very valuable skill. And it's not easy, it can be difficult, and you're gonna have to make some guesses here and there, and it's not gonna be trivial. But if you read a paper, being able to code up the model from that paper is really, really valuable, especially if you go into research, right? This is a valuable skill to have. And this is a good example, I think, because here we have the image from the paper, and here you have my implementation, right? And there's a couple of things that you could argue that you could do slightly differently, but this is my take on it, and we'll get good performance from this model. And it's gonna be pretty similar to what Jan LeCun did. So here is the implementation of this neural network in PyTorch. So this is the first time you've seen this. This is this inn.conv2d, conv2d. So this is a 2D convolutional layer as opposed to a linear layer like we've been using earlier. And let's kind of talk through the various parameters here. Maybe I'll pull up the doc string in a second, but I kind of want you to, let's take some educated guesses to kind of get a sense for how this works. And since I wrote this, I've started using that spacing. I don't know. All right. So here we go. So what do you think this 1 is doing? What are we telling our neural network? Well, any guesses? What is that first 1 in this conv2d argument representing? Yeah, number of channels, right? So if this was a color image, this should be 3. But this is a grayscale image, so it's 1. Okay. The 6 represents the number of kernels. We want to make 6 feature maps here. You know, if this was 8, we would make 8 feature maps, for example. Kernel size, I hope that makes sense. This is a 5 by 5 kernel. I believe you can have rectangular kernels, I think, but almost no one does it. It might be interesting. But this is a 5 by 5 kernel. Does anyone know what this is? What is happening here? What is this tanh thing that I'm doing? Yeah, this is our activation function, okay, right? And it's not a ReLU activation function. Well, that wasn't quite invented yet, and we'll get into that later. But Jan LeCun used a tanh activation function. What activation function have we been kind of using mostly in this class so far? What have we seen a bunch of? The sigmoid, right? So tanh is very, very similar. It just has a little bit different of a range, but very similar activation function. So here's the pooling operation. this 2 means it does it by a factor of 2. So that's that pooling operation, what Jan LeCun called subsampling. Here's our next convolution. So we have 6 input layers, right, or 6 filters, right? From here, 6 feature maps, and we're going to go up to 16. So notice there's 16 feature maps now. Again, it's a 5x5 kernel, which is, it's not indicated here, but it's explained in the paper that it's a 5x5 kernel. And then a tanh layer, which again, the tanh is not shown in this figure, but it's explained in the paper. And then another pooling layer. So here's that pooling layer here. That gets us down to 5x5, or yes, 5x5. Yeah, so Hernan asked a really good question. Why is this here, right? How does the activation function help the neural network? Really great question. Does anyone know? Why do we use activation functions? Yeah, so yeah, exactly. So Hernan, this allows us to learn nonlinear patterns. It's a great question, Hernan. I'm glad you brought it up. What would be fun, Hernan, is go try to train this without the tanh, right? I don't think it will really learn very well. It lets you learn nonlinear patterns. That's what the activations let you do. If you think way back to the first neural network lecture, we talked about kind of dividing an input space into 2 regions, and we did that with a line. By using activation functions, we can use more sophisticated dividing surfaces between the things we're trying to classify. That's in higher dimensional space, but it allows us to learn nonlinear patterns. Great question. Okay, I'm not going to focus on this line too much, but I want to point this out. This is a very common pattern that you'll see all the time. And Austin has asked a great question here. I'll get to that in 1 second. Great question. Let me make one more point, and then we'll look at Austin's question. So the first 2 layers of LayNet 5 are convolutional, right? And then we switch to fully connected, like we would have before. So we have 2 convolutional layers and 3 fully connected layers. This is a very common pattern to use. And it is less popular than it used to be, but it's still very popular. It's the ResNet model you would have used recently has this pattern. So we use linear layers on the end. There's a few reasons we do this, but really what it lets us do is it kind of lets us get the best of both worlds. So the convolutional section is often called the feature extractors. We'll see kind of what these do shortly. And then this part of the network kind of makes a final decision. That's kind of how I would think about it. But that's just my interpretation. We'll get into it into more detail. But we've got 5 layers here. This is how they're set up, and this architecture matches Jan LeCun's architecture. So Austin has asked, is it 16 filters per 1 input filter, or 16 filters in the total from the 6 input filters? Yeah, so Austin, this, if you think about in your head, right, think about what this is doing, right? This is kind of interesting. It's kind of hard to think about. So what's really happening here is now we kind of have an image. We have this new image, but it has 6 layers to it, right? So if way back here, right, we talked about how when we do convolution, we have these filters, right? And this is why I made this point. So these filters, the depth of this filter always matches the depth of the input. So the input could just be an image, or it could be, you know, the previous layer from a neural network. So in this case, what our filters really look like in this layer here is they're 6 deep. So our little kernels are 5x5x6. And you have 16 of them. I hope that makes sense. So this is really making a layer that has 16 kernels that are 5x5x6. Good question. Okay, cool. So let's get into it here. Let's go train this sucker. We have to do a little bit of reshaping in PyTorch. I think I'll keep moving past this for now. I'll come have a look at this later if you're interested. It's just some data shaping to get things to the right dimension. I'm going to make a data loader. And yeah, we're going to train. So I don't know how fast this is going to be. We'll see. I've kind of given away the conclusion here. We end up with around 99% accuracy. This might be a little slow. I might keep talking. Okay, now it's kind of going. So already after 1 epoch, we're at 93.8% accuracy, which is pretty good. And this will get up to around 99% accuracy. So let's see here. And let me go ahead and answer this question, and then we'll, okay, yeah, perfect, great. Okay. So Nick has said, how does the Conv2D layer deal with images of different sizes? Yeah, that's a great question, Nick. It seems like the layers deeper in the network depend on the input image being a specific size. Yeah, so Nick, that's a great question. All right, so let's go up here. So notice this 256, right? So this really depends on, it's basically when you unravel all these, this is doing an unraveling, It takes all these feature maps, puts them in a huge vector. That vector ends up being 256 long. So if this image input size doubled, right, then this would be different, and you actually would break your neural network, right? So in Torch, and I believe in FastAI as well, there's this idea of adaptive pooling, and I can't actually do autocomplete right now because I'm training. I may stop that. So yeah, we're at 98.4%. This will get to around 99%. So I'm going to stop that training. And yeah, I just want to show you this method real quick because it's important. Yeah, so there's this idea of adaptive pooling. And in practice, what we'll do, Nick, usually is we'll use, instead of just using this kind of lambda function thing, and you'll see this, I think we'll get to it today, we'll see, but we use what's called adaptive pooling. And what adaptive pooling does is it takes an input data block, just like any other pooling layer would, but instead of just downsizing by 2, it actually can downsize any input to be a fixed output size. So what I can do here, I believe, I forget how the syntax works exactly, but yeah, output size. So if I do like 5 by 5 here, no matter what the input size into this layer is, the output will always be 5 by 5. And in practice, you probably would go bigger than that. Like maybe I want to get it down to 16 by 16 or something. And that's the idea here. So this can handle different image sizes, but LaneNet 5 cannot, right? But the trick with modern neural networks is to use something like this. And what that does is it always makes the output, and it does pooling, but it does pooling to make the output. It can dynamically change the pooling rate, basically. So yeah, great question. We haven't broken away from having, we can't yet have different sizes. LaneNet 5 is still fixed to one size, but as soon as we introduce this function, adaptive average pooling, then we can have different sizes. Good question. Okay, so what I'd like to talk about then, so I've shown you all this stuff, right? So I've shown you, here's a bunch of stuff that existed in 1998, right? So 22 years ago. As you may know, deep learning didn't really take off in the 2000s. Neural networks weren't really popular until like 2012. We'll talk about why as soon as we have time. But what I really want to get into is, what's different, right? So a lot of the stuff I just showed you, like, really hasn't changed. Like all the stuff that Yann LeCun was doing in the 90s, was, it really is common practice today. So like, why didn't deep learning take off until 2012, right? Why did it take so long? If you read some of the literature, there's some kind of jokes out there about how back in the old days, like Yann LeCun was the only person who knew how to actually train these things, and he was just like a neural network wizard, which there's probably some truth to that, right? But yeah, so Abhijit has mentioned something important. So compute power. So compute power is a big piece of this. When you really look at it closely, though, it's not just compute power, but that's a big important piece of the puzzle for sure. But I just want to point out that, a lot of the pieces to make deep learning happen, they were there in the 90s, but no one really knew about them. And we didn't quite no one had put all the pieces together yet to make this a really popular modern technology. So I think that's fun because if you think about today, right, what technology is just sitting around today that no one really cares about, right, that in 20 years everyone's going to freak out about, So there are technologies today, I don't know what they are, right? Let me know if you figure it out, but there are things out there today that will become very popular in 10 or 20 years, but they're still kind of hidden just for different reasons, right? So I think it's really interesting to look at the history of where these things came from, because most of the ideas were really there in the 90s. Now, compute power is part of that, though. That is part of the puzzle. But really a bigger part of the puzzle, in my opinion, is really the data. Let's get into that now in a little bit more detail. So I'd like to tell you a quick story of this researcher named Fei-Fei Li. So she, back in the mid-2000s, she was a computer vision researcher. I think she was a professor at the University of Illinois. So she decided around 2006 that she was going to create the world's biggest labeled image set. There's a great article on this you can go check out if you'd like to. So her first idea was, she said, okay, let's go make this huge labeled image set. And it sounds kind of obvious today that making a labeled image set would be helpful for computer vision research. But it was actually very unpopular at the time. So no one thought that the trick to making computer vision better would come from having really, really big data sets. That was not obvious to most researchers. So she had this idea to make, this huge data set. Oh yeah, I don't think I've seen her TED Talk. I should go watch that. So you guys, so Sai recommends it. So yeah, if you guys want to check out her TED Talk, I haven't seen it. I should go watch it myself. So back in 2006, you know, she went to make this data set. Maybe I have, I might have seen it, I can't remember. But anyway, I bet it's great. So yeah, she has a TED Talk. So she hired undergraduate students to do the labeling at first, which did not go very well. So then she started using Amazon Mechanical Turk, which had just come out at the time. And she published her first data set in 2009. And at the same time, she published her and her group published a challenge to academics. They called it the ImageNet Large Scale Visual Recognition Competition, the ILS VRC. And for that challenge, they released around 1.2 million images for training, and about 100. They kept about 100,000 for testing. And those images had around 1,000 different classes. So I made this little video because I want to show you kind of the scale of this image data set. It's hard to think about a million labeled images, right? Kind of hard to think about, I think. There we go, cool. So what this video does, and I'll go ahead and start playing it now, it's kind of long. This is a 5-minute video, and if you watch the whole video, you will have seen every single image in ImageNet. So they're all here. It's a 5-minute video. And I've had them categorized by class. So like, you know, ice cream, I'll pause it for a second. So we're on gong. So here's a bunch of images of gongs, right? I'll play it again, pause, volleyball. Here's a bunch of images of people playing volleyball. I'll play it again, I'll pause it. Here's bighorn ram. Here's a bunch of images of rams. So what I think is kind of fun is, you know, when a deep neural network is training, right? And we know it's trained in epochs, right? So we have multiple passes through the data. So the video you're watching now, this is one pass through the ImageNet dataset. So this is what it feels like to be a deep neural network, right? These are each like a mini batch, right? And we're going in order, right? In order of the classes. In practice, they'd be randomized. But this is kind of what it feels like to be a deep neural network that's learning, right? So you get these batches of data thrown at you. This is miniskirt that I stopped on. Warthog, there you go. So hopefully this gives you a little bit of a sense for what the ImageNet dataset looks like. And each image is classified, again, with one of 1,000 classes, and you're seeing the class on the bottom. And yeah, if you watch this video, if you watch the whole thing, we've made it through a minute. It's 5 minutes long. You will have seen all of ImageNet. So, of course, not in a lot of detail, but that is the ImageNet dataset that she constructed. So this is kind of what happened in that decade after Jan LeCun's work. So one thing, important thing that happened is Fei-Fei Li created this data set. Yeah, so Sai asked a great question. Could you ever overfit on a data set that big? So yeah, Sai, you actually can. It's kind of remarkable. It's a great question. So I think Sai is kind of asking, hey, you know, this data set's so big, would it be possible to ever overfit on it? And yes, you can, which I know sounds crazy. I think it just speaks to how powerful deep neural networks are. Okay, so they published this data set and this challenge, the ILS-RVC challenge. And this challenge turned out to be very difficult. So the way it was scored, you know, you submitted your algorithm and it was evaluated on 100,000 test set images. And you were actually given 5 guesses. So you could take 5 guesses at each image. And if you got any of your 5 guesses right, you were counted as correct. And the very best submission in 2010 had an error rate of 28.2%. 28.2% was the error rate. So that is not great, right? So not tremendous performance, right? In 2011, performance improved a little bit. Let me zoom in here just to make sure you can see. Performance improved a little bit up to 25.8% error rate. So getting 1 out of 4 wrong, something like that. And these approaches did not use deep learning. They did not use deep learning. So what happened then in 2012, and I think this is really the origin of modern deep learning. So Geoff Hinton, this guy we talked about back in the 80s, right? His group struck again. So they released a paper called ImageNet Classification with Deep Convolutional Neural Networks. This is often called the AlexNet paper because of Alex Kravinsky, who is the lead author. I think this is Alex back here, I believe. So they published this paper, and they dramatically improved performance using a deep neural network trained on GPUs. And again, using a lot of the same tricks as Jan LeCun, but some new stuff. But this really is the beginning of modern deep neural networks. Back in 2012, you know, I was in grad school kind of working on machine learning stuff. And no one was talking about neural networks. No one cared about neural networks. It was not the thing, right? No one was talking about deep learning. And really this paper was when people's opinions started to change. And also back in 2012, the AI was not a popular term at all. AI was not a marketing term. No one was using it. So a lot has changed in 8 years, and this really is, and work was happening before this, but a lot of people see this as the inflection point, the point when things really started to change. Yeah, Hadoop was a big deal in 2012. That's true. Everyone was talking about big data. That was like the last trend before AI was big data, right? And yeah, Hadoop was Hadoop was cool. It still is cool, but it was really cool in 2012. That is true. Good memory, Monica. All right. So Jeff Hinton and his team reduced the error rate down to 15.4%, and it kept getting better. We'll get into that in a minute. But here's the figure. Here's the figure. So I showed you one architecture diagram from Jan LeCun. Way the heck up here, right? This is from 1998. Here is the figure from the AlexNet paper of the architecture they used. Here it is. So let's talk about this picture. There's a lot to be learned from this picture. First of all, they're using bigger input images. Here's the input image, right? So you can see the dimension is 224 by 224. Apparently that's a typo. It's actually 227, but it's not a big deal. They're pretty big. You have bigger kernels, 11 by 11. Notice you have color images. It's a depth of 3, right? And this is the network, right? And if we count the layers, it has 1, 2, 3, 4, 5, 6, 7, 8 layers, which is really a big deal. In 2012, no one had really succeeded with this depth of a neural network. Next, I would like you to notice that the top of this figure is cut off. Like, where's the top, right? This drives me crazy. It's not an error in my notes. It's actually an error in the original paper. So one day I'm going to make a non-cut off version. If anyone wants to make one, please send it to me and I will use it instead. But the original paper had an error. It got cut off. The next thing that I think is really interesting, notice that the input, here's the input, right? It's split into 2 pipelines. So here's a pipeline on the bottom, and here's a pipeline on the top, right? Does anyone know why? Why did Alex Kravinsky, when he worked on the AlexNet paper with Jeff Hinton and his collaborators, why did they have to split this into 2? Or was it, why? Why is this network split into 2? Any ideas? So Hernan guesses 2 neural networks. It's actually really 1 neural network. It's a good guess. But this is really 1 neural network because of the way it's connected. And it has 1 loss function, 1 input image. But they had to split it in 2. Any other ideas? Okay, so Abhijit's getting warm, right? So it's not that one's on the CPU and one's on the GPU, but that's a good guess. It's a really good guess. I'll make one little comment. Well, let me put it back to the class just for another second, right? So parallel, sure. So as you may have noticed, when we're training on a GPU, one of the big limitations is the amount of RAM that we have in the GPU. And I believe that AlexNet was trained on an NVIDIA 580 GPU, I think. Maybe it was a 380, something like that. So a very old GPU by today's standards, right? And I think the GPUs they used only had 3 gigabytes of RAM. So to actually really train this thing, they had to split the network in half to fit on 2 GPUs, which is kind of crazy, right? That's the only reason. It's the only reason. It's just because of the compute they had. So it has 2 paths to fit on 2 GPUs. Okay, there's one more thing I'd like to ask you. Notice the output dimension, right? What is the dimension of the output for AlexNet? What do you see? 1,000, right? Why is the dimension of the output 1,000? Yeah, there's 1,000 classes. Yep, perfect, great. Okay, so we're almost out of time, but I kind of want to get into the next thing with you guys, because the next thing we're going to do, and really kind of our last deep dive into deep learning, we'll finish next lecture, is to really walk through AlexNet in PyTorch. I want to give you the best sense I can in PyTorch of how AlexNet really works. So we'll start now, and then we'll stop in about 5 minutes. But what I'm going to do is I went ahead and downloaded AlexNet. So there's a pre-trained AlexNet you can download as part of Torch Vision, which is the Torch computer vision library. And here is AlexNet. Here it is implemented in PyTorch. It's a little different than Alex Kravinsky would have written it the first time, right? But here it is. It's not split into 2 paths because we can fit this on modern GPUs, thankfully. But here it is, right? So let's kind of walk through it. So you see your convolutional layer right here, just like you would have seen in LayNet. Now what is this? We'll talk about it in more detail in a second, but does anyone know what this ReLU thing is? Yeah, so this is the activation function that Alex Kravinsky and his collaborators decided to use. And it's a little bit different. I think we'll talk about it down the page. I forget where, but we'll get to it. But it's a little bit of a simpler activation function. Here's your pooling layer, just like in LANET 5. Here's your next convolutional layer. Here's a ReLU. Here's a pooling layer, convolution, ReLU. No pooling for this layer, convolution, ReLU, convolution, ReLU, pooling. And then we have, so remember I mentioned that adaptive thing? I don't think this was part of the original AlexNet paper, but the PyTorch implementation today uses adaptive average pooling. And what does this allow us to do again? What is the advantage of using adaptive average pooling? Different image shapes, perfect. So AlexNet can work, this implementation of AlexNet can work with different image sizes. Perfect. Okay, we haven't talked about dropout yet, which we will. We'll skip that for now. So here's a fully connected layer. That's the first fully connected layer of AlexNet right here. Dense layer is what they call it in the paper. We have another ReLU, a dropout, which we'll talk about later, a linear fully connected layer, a ReLU, and then finally a linear, landing us on 1,000 output values. So that is AlexNet in PyTorch. I hope that makes sense. So, and this is the neural network that brought around the modern age of AI, which is pretty cool, right? So this network has been talked about and worked on a ton in the 8 years since it came out. So what I'd like to do with you now, just to give you a deeper sense of what's happening with AlexNet, is I want to take an image and I want to follow that image through AlexNet. I want to take that image and let's go step by step and let's see, what is AlexNet really doing to that image to make a decision. It's really, really cool. You can actually get fairly deep into these things. So that's what we'll do now. So I found this cool image of a golf ball. Here we go. And I want to pass this through AlexNet. So first I have to do just a little bit of pre-processing. This is not too exciting. I resize it, I make it into a tensor, I normalize it. Basically I subtract the mean of the whole data set and divide by a standard deviation. Nothing too exciting. What I really want to get into is what happens when we pass this into our neural network. So I'm going to pass it into AlexNet, and there's a little trick I do to change the dimension. Again, just review that later if you'd like to. Not too big of a deal. And at first, I'm going to actually go ahead and pass it through the whole thing. So before we go layer by layer, I want to pass my image through the entire thing. And I'm using this torch.noGrad thing. Remember that this is if we don't want to actually update our gradients, and we don't want to do that when we're just doing inference, then we use this torch.noGrad thing. So I compute this y hat thing. So this is y hat. This is the output of AlexNet, and its dimension is 1 by 1,000, which I hope is not surprising. And if I plot it, this is what I get. This is what I get. This is the 1,000 outputs, the 1,000 numbers, right? This is just a line plot, right? So every single point corresponds to an output value of AlexNet. There's 1,000 of them. What are we looking at? So when you look at this plot, right? Is this what you expected? Why is this y hat, right? What should we do with this, right? Well, any thoughts? Are you surprised by what you see? Why is this the output of AlexNet? So yeah, Monica says 1,000 classes, right? What would you do? What would you need to do with this output to get something meaningful out of it? I mean, I think probably you're hoping, it's an image of a golf ball. You're probably hoping that the neural network says golf ball, right? But instead you get out this long vector, right? So what do we have to do? What's going on? So yeah, Hernan says some of them are negative. Yep, absolutely. So yeah, Monica says, hey, that one around 580, maybe that's the answer, right? Maybe it's the max, right? And yeah, Monica, that's a big important part of the answer. I want to address Hernan's question real quick. So really, if you look at our neural network, let's go back to AlexNet, right? So let's look at the output, right? The very last thing in AlexNet is a linear layer, right? So a linear layer, that's just a matrix multiplication. So a linear layer can result in positive values, negative values, all kinds of stuff. Sometimes we use a sigmoid function on the output, right? When we're doing single class classification, right? What did we talk about using on the output last time instead of using a sigmoid, for example? Do you guys remember what kind of output activation function did we talk about using for classification? Softmax, yep, perfect. And it turns out it's actually way more efficient to implement the softmax function in your loss function because of basically logarithms than it is to include it in your network. So traditionally, you actually will not include your softmax function in your network. It's actually considered usually part of your loss function. So for that reason, we can get outputs that are scaled like this, right? But to really get them to be something a little more meaningful, we want to take a softmax. So what I've done now is I've taken the softmax, right? And now you can see we have, hey, one really nice big spike. And we'll wrap up in 1 second here. But all we have to do now is we say, okay, what is the index of this spike? So Monica guessed 580. Let's have a look. It's 574, so that's a pretty good guess. And we have to grab the ImageNet labels. So I've included in this repo ImageNet labels.txt that has basically just a mapping where it says, you know, label 1 is this, label 2 is that. And actually, instead of just me saying that, let me just show you, right? So we have this index to label thing, which is a dictionary. And we'll wrap up in one. Why can't I click on that? That's weird. My mouse is being a little weird. IDX to label. Cool. Yeah, there you go. So here's our mapping, right, from indices to labels. So class 1 is a goldfish, great white shark, blah, blah, blah. So if I scroll down, let's see, we want to go to 574, scrolling. And of course, I can just sample it in a second, but I just want to see. If I go to 574, we're hoping for a golf ball, and we get, let's see, golf ball. All right, so there you go. So it has predicted the right thing, but it's worth paying attention to how it makes that prediction, right? So it's put a high signal in that unit that corresponds to golf balls, unit 574, and that's how it makes a prediction. Okay, great. So I hope that was helpful. Next class, we're going to dive into a little bit deeper into AlexNet, and then finally, we're going to talk about generative adversarial networks. So make sure you look at your reading for this week. You know, I want you to look at the AlexNet paper. You should have had a chance to do that already. And then have a look at this Goodfellow paper on GANs. That will make next lecture a little bit more informative. So I hope you guys have a good week. We will talk to you on Thursday.